Okay, just testing that it's all live. Okay, it looks like it's gone live now. So I'm going to hit testing here as well, just to make sure. And I haven't got a splash screen, so this is the splash screen, which is actually a book that I wrote, which is the Python programming book. It says Hello World over here. And it's called Top of the Stack Python Programming. So you can go and get it on Amazon. Aside from that, let me just close down some systems because I don't want any background noise. And right, let's move on. And I'm going to look at this piece here, which is, well, I'm going to look at a couple of bits. We were on neural networks and we were actually talking about backpropagation. So this was the actual website that I was looking at. And in fact, before we do this web link, there was another page which I was looking at, which is this page over here. And that's kind of like, this page here was chapter 2. And that's kind of like where we sort of like kicked off. But actually, you know, preceding it is chapter 1, which is this page here. And just sort of like, it's a good recap. And kind of like what are we actually even trying to do or achieve? We're trying to make this neural network, and sort of like how do we recognize the digits? So if I actually zoom in a little bit on this, because I know that sometimes, let me see if I can zoom in, Control plus, yeah, there's some zooming. How do we recognize these digits? Basically, it's sort of like the crux of everything. So at least how does the computer do it? So in our brains we've got this neural network that does it, and we want to replicate the same thing, some sort of learning process. Now we could give a rules-based approach, but that would be us as humans coding. So we don't want to do this human-based approach anymore, because there's some things that are really complex and it's going to be quite a tough thing to do with, like, you know, tons and tons of rules. So now we're moving on to, and this is for all of these large problems, something that's more like a neural network type of problem, a solution effectively where the computer just goes and does something effectively, something that replicates our brain, a neural network, and it comes along until, like, we can train it on this large amount of data with all of these, like, for example, if I highlight these things here, like all of these number ones, like they all look slightly different, but we can agree that sort of like, you know, as a human being, these would be all number ones. And, you know, can the computer do this? And, you know, what is shown is that not only can the computer do this, the computer can do this in, you know, less than 100 lines of code. I think even in here. And there's loads more of these ones. And in fact, as a human, I might miss some of them. And we can see, like, this one, for example, slightly different than the other ones, which are just lines. And we might think that's a 2. You know, and be like, so like, what interesting, like, you know, does a computer think that's 2? And this, for example, this 7 here, well, what I'm calling a 7, might actually be a number 1. So again, can the computer decipher that? And here's another one. You know, we could agree that I think this is a number 1. But then we could contrast it to this number 1 over here. Anyway, save me drawing all of those things. That's kind of like what we were trying to get to. You know, there was something 74 lines of code. It's a bit deceptive when we say 74 lines of code, because in Python programming, you know, when we do one import, so for example, let me just remove some. Well, in fact, I've got an import here, for example. I've got a few imports, but when we import one of these modules, we can actually, it looks like one line of code, but if I go to definition and sort of like open it up, this is the actual requests module, and, you know, it's in fact it's going to be bigger than that because it's referring to C stuff as well. But you know, that's 180 lines of code, but it's actually much bigger than that as well. So, and we can keep drilling down. In fact, maybe, I don't know, if I go to definition there and sort of like keep drilling down, import warnings, import URL libs. So, you know, go to definition. So that one library is importing from another library, which is importing from other libraries. You know, and these things in, like, the, you know, the bottom line of it could be many thousands of lines long for these neural network types of code. So it's kind of like a cheat saying it's just 75 lines of code. This isn't the code for that. This is the code just for scraping stuff. So something completely different. Maybe I'll even delete it. It was a Stack Overflow question. But you know, again, here's, you know, sort of like an import Plotly Express, and you know, we just wanted to print a chart out, and here is our chart printing thing. But actually, the back end of it, which looks like one line of code, there's an immense amount that is actually done in the background before creating it. So our front end is 74 lines of code. Anyway, this isn't a coding thing as yet, although like most of the stuff that I do is coding. But the key bit is that the program can recognize digits with an accuracy of over 96%. You can imagine a slightly better one, algo. I don't know, that's, you know, a few hundred lines of code to quite easily achieve 99%, or can we achieve 99%, or even better. And you know, the pieces that we might not get in that is, for example, like, is this a 1 or a 7, or is this a 1 or a 7? Those things where it's actually ambiguous to both the human and the computer as well. I should also say actually that the author, well, we can see it down here anyway, so thanks to the author, but he's actually written this in 2019, we're in 2023, so this is somewhat 4 years old, but it's a great point to start with anyway. I could have picked many items, many different articles, but this one was quite a good one. And yeah, that's kind of like it. So that was kind of like the background of it, the real background. And I think I touched on that at the end of the last session because I just felt that I needed to go back. But I kind of got up to this bit. So I did a little bit of reading on this actual site just to remind myself and to like catch up as to where we were. And the other piece is I reopened up this, which is my maths notation thing. And let me just hit actually on here because refresh. Sometimes the table like changes its formatting, so I had to muck around with that. But so I went to reopen it. But anyway, I added this piece in here, and again I'll do a zoom in if I can, so that it's a bit clearer. But we had this, and we had this back propagation notation, which we are back propagation notation. That's quite a mouthful, or quite poetic back propagation notation. But we had this notation where we wanted to, or at least we had these layers. So here are the layers. Over here we've got the layer L over there, and then we've got this previous layer over here, and we've got the next layer over here. And our layers kind of like move sequentially, sort of like in this order. We're migrating this way in terms of our calculation, but we're going to do some back propagation, which actually goes the other way as well. But in order to do all of this, we need to sort of like identify a neuron effectively, and also we needed to identify the weights and the biases. And we started off with the weights, so I'm going to hit delete now just because I need to scroll down a tiny bit on that. So let's get rid of all of that imagery. We defined a weight W, L, J, K, so there was lots of symbols there. There's 4 symbols in that, so like, what does it mean? And there's a weight which has a value, and it was of the kth neuron, and it was we mentioned something about this, that like we say J and K, and surely like we should mean J is on the left hand side, so surely these should be all the J's and these should be all the K's, but the notation is the other way round, such that these are all of the J's and these all of the K's. And I think there was a reason for it, which we were just touching on at the end of the last session as well. But that's just basically the notation, and it's telling us where what we're actually talking about mathematically. So 5-1 is talking about this number 1 here is referring to the first index item of in our layer. This top piece here is actually the layer, and we're talking about, so this is layer 1, this is layer 2, so this is layer 2, just in our sort of like indexing. This is layer 1 and this is layer 3. This was just sort of like a grid. You could imagine it as a grid, and I sort of like did mention it's sort of like a Cartesian thing, you know. And if I told you like 10, 5, right, you'd go 10 across, so you'd sort of like count 10 across, and then you'll count 5 up, and you'll sort of like put your X somewhere over there, for example, and that's 10, 5, right? So this is the same sort of thing. It's just saying, like, what is this W? So this W is referring to layer 2, and it's actually referring to this, which is the kth item. So it's index number 1, and then 5 elements down. So 1. Again, this is here. It's 1, 2, 3, 4, and then 5. So it's the 5th index down. And that's what that 5 refers to over here. So that 5 is referring to this, and that number 1 over here was referring to this, k equals 1 and j equals 5. So we now had some notation basically to talk about, at least so that we could all agree, like a framework, so that we could all agree of what this W of what this weight actually is, the value of the weight, and the W is actually a value in itself, so it will be somewhere between 0 and 1, which is, you know, the typical values for the weights, and I don't know, like 0.75 or something, and it will be 0.75, but it's specifically applicable to this. And if we were talking about a different line, it would have different indices effectively. That's how we're going to reference it. Very similar to how we reference the Cartesian coordinate, but how we reference our Cartesian coordinate over here, but we don't just have x and y's, we now have j, k and l's. So 3 things. We're describing how far across we're going over here, and then we're describing 2 other parameters, because we need to find that item and also one of these as the link between 2 parameters. So, you know, it could be between this one and, say, for example, this one. So that's what this WLJK is talking about. It's to say, again, go to layer L over here, and then also we're talking about this particular item here, like the 2nd index here and the 5th index here, and that would be written as W. Again, it would be 2 here, and then this is 1, 2, 3, 4, 5, 6, 7. So it would be a 7 over here. And then here that will be 1, 2, so 7, 2. That's the description of this particular weight. So that's it. We've got some mathematical formalism falling into place, which is quite nice. So we did that. And also, well, here we did mention it, one quirk of the notation is the ordering of the J and K indices. And I can't remember if I went into that, but maybe we'll get a reminder of that. We also have a cost function and weights or bias. Okay, and we are seeking the rate of change of the cost function. The cost function is this thing relative to the end. So we saw that we get some cost of doing this, and this cost was like effectively the error, like the error rate that you could measure. In terms of changing these weights. When you change these weights, you end out with some kind of like guess at the end. So over here we're sort of like, you know, that's finally producing, this is our guess, right? There you go, guess. But you could guess like 100 times effectively, or 1,000 times, and you can sort of like measure your error rate in your guesses. I wonder if I actually got a line somewhere over there which makes my thing a bit wider. Let's have a look. Somewhere here, there you go, I've got a spurious line I spotted. Delete, save and close. That'll make my image a little bit wider, I think. There we go, moved on to the next page now. Made it a bit longer as well. So let's just shrink that down a tiny bit. I wonder if I can get that onto the same page now. Maybe it was actually good having that little line over there. But anyway, that's kind of like, that's what it is. So we have the same thing for the biases as well. So we've got this cost function. That's what we're trying to do. And we're trying to establish, at least we're going to try to establish, how this cost function changes with respect to changing these weights over there. That's what it is. And presumably, but I don't know yet, but how this cost function changes with respect to changing the biases. But maybe the biases are computed from the weight, so that's fine. But that's basically it. So again, we've got some notation, and the other part of it is actually a similar notation for the biases, and we sort of like where here we needed, when we had this, we needed a 2nd index down the bottom because we wanted to say like it's, and I should actually really in a way could maybe even over here, I could do another version of this, so like tab it across, paste that in, and this is actually K is the start, right, and J is actually the stop. Right, we're going from the starting neuron to the stopping neuron, and L over here is actually the layer. Right, so you know, oh, autocorrect. There we go, fantastic. So it kind of like looks like that really, and W is the actual weight. So that's kind of like the big version of what that looks like. So in the oddity, it's basically the start goes second rather than first. So like you got your stop point and then your start point. You kind of want to. We can see where like why this might be logical is you sort of like want to know where you end, and the weight is pointing in a certain direction from a start. So you look, you've got your starting point and you've got your ending point, but I actually care about the ending point. So this is the actual point that we care about, which is this. So whilst we do care about the start, we sort of like we really want to know to be able to compute, or the weighting to get us towards this ending point from this starting point. So you know we're always referring effectively to the ending point, and I guess that's why the J bit came first. So we needed to know the layer, because you need to know what layer you're in, and then you need to know the that's a comma, and then you need to know your J point there. Well, that looks terrible, so I'm going to have to do that. Basically, you need to know your layer over here, and then comma, and then that's a worse comma again, but J. So that's kind of like what, you know, that this LJ here identifies this point over here, and this point here now is just basically K, and it's L minus 1 over there. So we didn't need to, in our notation, we didn't need to say layer and then layer minus 1, because it's automatically taken that, given that we know what L is, that the second bit is just L minus 1, it's just the preceding one, and so all we really had to specify was this start index over here. So that's an L minus 1 and K. And you could like see this, like here you go, there's your Cartesian looking coordinates, or the way of referencing, or the notation, and that's our sort of like end point over there. So many different ways of describing the same thing, but we need to understand this because it's fundamental in the mathematics. But anyway, we'll go back because we've got this similar notation, and that's kind of like why I jumped to the top. It clears it up a little bit because you've got your bias, and then you've got the layer L and the index J. So we sort of like know where to go. So, and over here, this is B. The layer is 2 because it's, again, we've got 1, 2, 3, and notice one thing, like normally in computing we start at 0, so normally it's 0, 1, 2 for computing, 0, 1, 2, but here, so far at least in the notation, we're using, at least that document's used 1, 2 and 3, and likewise for our counting of our vertices as well. Over here we've got a 1, well I should colour that one in, I'll do an undo quickly on that one, but computationally we'd normally say 0, 1, 2 and so forth, and then go to like n minus 1 over there. But the way that the notation in the book does it is it goes 1, 2, the book or the article, 3, and it goes all the way up to n. So just something for notation, and so long as it doesn't matter which one we do use, but so long as we can agree on it, then we can have our notation we're using. We've got a framework for discussing things, and that's the whole point. And that's mathematics, by the way. That is mathematics. That's the mathematics of computing. Well, mathematics of computing at the index 0, but like that is the mathematics or the mathematics of discrete maths. So let's just go and we're going to look at some formulas. The formulas connect or show relationships. Okay, yes, so the formulas here, I'm reminding myself of what I wrote, but the formulas connect or show relationships between the nodes of the neural networks. That's what those W's do. and these B's over here, these biases, are actually the values of the nodes, I guess. And that's kind of like where we stop. So that's all like recap over. I don't know how many recaps. Let's have a look over there. I wonder how long we'd be running for. Yeah, a 20-minute recap. That's long enough for a recap, I think. And I'm going to go back then, so and have a little sort of like refresher of a little bit more. I read this first paragraph, and again, everything's going to be new to me, or a massive reminder, because the last time I read this was probably a year or two ago, if not longer. So let's just go back and have a look. But so perceptrons is the title of the next piece of the first chapter. What is a neural network? To get started, I'll explain an artificial neuron called a perceptron. So one of these little circles here is very, very much equivalent to one of these little circles here that we're talking about, and sort of like it's getting some information from all of these preceding perceptrons, should we say, over there. So let's make sure. Today it's more common to use other models or artificial neurons in this book, and in much modern work on neural networks. The main neuron model used is called the sigmoid neuron. So we could go and Google sigmoid, but I'm just going to go into like say that a sigmoid function looks something like this. There we go, that's like our sigmoid function, or in fact, if I do an undo, so it's not passing over the line. But it's something like, it's an S shape, and it's like in the middle. It's sort of like how it is the decision boundary in some way. So as to whether that's like off or 0, and whether that's on, which is a 1. So that's kind of like, there's our boundary in the middle. So that's kind of like what that's referring to. We'll get to sigmoid, there we go anyway, we're going to get to sigmoid neurons shortly, but to understand why sigmoid neurons are defined the way they are, it's worth taking time to first understand perceptrons. And there's more things in sigmoid as well. Sigmoid is one function, there's a couple of other ones as well. I think the sigmoid is probably one of the easiest ones, not that the other ones are that difficult, to be fair. So how do perceptrons work? A perceptron takes several binary inputs. It takes in this x1, x2, and x3 and produces a single binary output. So here's our binary output. In the example shown, the perceptron has 3 inputs, x1, x2, and x3. Great. In general, it could have more or fewer inputs. So, and in our one over here, God knows how many I had, but like if I take this B5, if every one of these is computing, well, that's 4 in our particular case. 1, 2, 3, 4 of them over here, but we could have had more in the previous layer. So it depends on the neural network and how it's structured. But let's just assume something relatively basic, which is we've got these layers, but we'll keep it quite cheap. We've only got 3 layers here. You've got a preceding layer, and imagine that you take inputs from every single one of them. Then the number of inputs that you're taking is the number of perceptrons. Now I'm going to call that a perceptron in the layer. So maybe I could add a little, maybe I will call it a perceptron. I'm just trying to think, is it a node or is it a perceptron? I've got to be careful. Maybe I'll actually even pull out Claude AI, and I might just do that. So let's start a new chat, and right, there we go. What is the difference between a node and a perceptron? Just because I'm building up here, and I'm going to do a control plus a few times. Different concepts in machine. A node typically refers to a single unit or neuron in an artificial network, which is like each one of those circles. It receives an input from other nodes from external data and performs a calculation. An input that their perceptron is a specific type of artificial neuron invented in 1993. It performs a linear mapping to the output of the threshold. A single perceptron and uses a threshold activation function to fire its output. A single perceptron forms a simple binary classifier and is often used as building block. So here, key differences. A node is a generic term. Perceptrons use linear mapping of inputs and outputs. I mean, you know, we could refer to them as either. And actually, one thing that I might do here is I will call. So I will actually open this up. I'll get rid of the little drawing on the side at this point because it's not sort of needed, and I'll put in a little piece of text here, and any one of these is sort of like that is a node, right? They are points to a node with a little arrow like that. That kind of points to the node, and just to differentiate that line from anything else, because it's not a line, we'll change the line color to sort of like there we go, sort of like greenish, and maybe there we go. So that's a node. That's probably why that thing got big last time. Hit delete, save and close. There we go. So there's a node over there, one of these. But we could also, I'm going to do it anyway. Turn rate perceptron, depending on what we're talking about. So I'll call it a node or a perceptron. But any one of these things is this node or perceptron that we're talking about. So, okay, we take these inputs, it does something, whether it's a node or a perceptron, so node is more general, it does some operation in here, and then it spits out an output. So the neuron's output is, or we could call it a neuron as well. I might add that too. Anyway, it's referring to Roseblatt, where some of this is taken from, but Roseblatt produced a simple rule to compute the output. He introduced weights, W1, W2, real numbers expressing the importance of the respective inputs to the output, and the neuron's output is naught, which is a naught or a 1, is determined by whether the weight, which is the sum of the Wi xj's, the wj's xj's from j equals 1 to n, like all of the nodes effectively, is less than or greater than some threshold value. And you can see here, like straight away, even in this really simplistic thing, if this one had a weight of 10, right, and this one had a weight of 1, and that one had a weight of 2, and this is kind of like the way to think about it. And I did actually watch a little video on this as well in the meantime, so I hope you, like whoever else is watching, did a little bit of research. But if this one's got a weight of 10 over here, then any change in this particular one, so here we've got like this result, right? Result, right? And I'll call that R for simplicity. But our cost is basically like the true answer. So like the true answer repeated 100 times minus the result, or the result minus the true answer. I'm not sure which way around it is, but you've got to get that right. But basically that's what our cost is. Now we can change our weights over here. So we've got a value, that each one of these has got a value, and I should actually move this weighting, because really the weight is here, is 10, 1 and say 2, for example. There we go, our weights are here, and then we've got our values over here. So I don't know, we start at equal values here, so say we've got 5 for everything here, so 5, 5 and 5. We can see that the change in the value over here is going to have a much larger impact, because this is contributing 50 into the system. That's 50, that's contributing, this next one's contributing 5, and this next one's contributing 10 over here. So we can see that a change in this particular value of 1 unit is going to have a much bigger change on the output. So this is going to swing it a lot more. And that's what we're looking at, this cost. So we're looking at this change. So the change in the cost, which is DC, the change in this particular cost over here, like how accurate it is relative to the W, the change in the weights. And so if we made this weight much less than the change in the cost, and we can sort of like, we get this like, I'm not good enough at drawing this, but we get this like theoretical slope. I can do it in 2D, so I can draw it in 2D, but you know, we're getting effectively a three-dimensional version of this like hill and valley. And you know, here, like, you know, it's very significant. This is meaningful over here because the slope's quite steep, and like here the slope is like less meaningful, but we want to know. So our weight over here is quite strong, it's meaningful, as in if we put a marble here, it's rolling down. Like the bias is very strong to rolling down. Whereas if we put a marble here, it might teeter to the left or teeter to the right. It's a bit more discussionary. But here, the bias is very strong for going down. So it's going to have this strong weight. So here it's going to have this weak weighting, and here it's going to have this strong weighting as to where you actually go. And so like, you can imagine that if we draw a second one, so like over here, you know, that maybe it's already going to start going that way. So this little change here is going to have this change in the weightings, like so moving from x1 to x2, should we say here, is going to change the slope from something to something else. So we want to know, and that is therefore going to change the cost function, and we want to know how that's basically changed. So we're going to do the whole mathematics of it. Anyway, so we've got these weights that are introduced, and yeah, we can do the sum of the WJ XJs. In fact, that's really what I did there. So if it all comes back, really, there's WJ, like 5 times 10 is 50. 5 times 1 is 5. 5 times 2 is 10. And then we sum them all up. And that is the sum of the WJ XJs, which is 50, 60, 65 in that case. And if we changed any one of these, it would change it. So if I change that to a 4 at the top, that 50 will become a 40. So it'd be 40, 55 all of a sudden. So the change in one of the, like one change in one of these has a disproportionate effect. And that's what this mathematics requires. So I might take some of this, because this is quite important. This is like the crux of some of the mathematics, should we say. Ah, I did actually have that open twice. That was interesting. Okay, so I've got that open here anyway. Let's just get rid of all of the stuff on top. The formulas connection will show relationships between the neural network. Want to achieve this, right, which is basically we want to achieve, I can actually splice this in, the neurons output 0 or 1, which is determined by whether the weighted sum, let's see if I can move across here, by whether, not that one over there. Okay, now I can put in my maths piece. It's less so basically here I can take the rest of it, and I will italicize this threshold value, because that's kind of like part of the key of it. So I'm going to put something in here. That's my ellipsis for the placeholder, but basically paste without formatting there. Some threshold value, and I'm going to steal his little thing here and put in, if I can, probably somewhere over there, italics, there we go, right, some threshold value. But in particular, we want to have, and now we sort of like, we understand a bit of our math notation. I'm going to insert a equation over there, and inside the equation we are going to have, I think, do I have it there? No, where is the sigma? There we go. Oh, that's a limit. Didn't want that one. Clicked on the wrong thing there, that one there, the sum. And I equals 1 to n, for example, for all of the neurons, and we might do wi, in fact, is going to be one of these, which is the WI, and then we are going to have, which is our weights, and then the neurons that precede it. So in our particular case, with our language, we're going to have the K, I's, and again, I'm sort of going to do that just to keep it all in it. Once it's built, again, K, I, like that. And that's kind of like the mathematical notation. That's sort of like the purest mathematical notation. Here he's used WJs and XJs because his input neurons are X's, but our input neurons were K's on our particular, like literally just in this particular thing. So I'm being consistent within the document here. But what I might do is insert a multiplication. There we go. So I don't know if it's, someone might argue that that's not the right thing to do. But we understand that WIKI is the multiplication of the of each of the indices from I equals 1 to n for all of these, basically, because it's n of them over here. So we're going to do that, and so each one of these is now going to have an output of 0 to 1, basically, some threshold value. So I wonder if these ones here, I don't know if you have to normalize them or not. You probably do. Well, you probably do have to normalize them, but they'll certainly be normalized anyway by the time they get here, because all of these will now have values of between 0 and 1, which is sort of like effectively the likelihoods. So again, in here is going to be a value between 0 and 1, and copy paste that and move that over there, and there we go. Save and close. Now I can get a little bit wider. Nice. There we go. So each one of these neurons, or each one of these nodes or perceptrons, like I said, we've got different words for them, but each one of these nodes basically will now have a value of between 0 and 1 according to the weights and biases of their preceding n items in layer L-1 of the K values. So I think I've said that like as well as I could have said it. Just like the weights, the threshold is a real number. Okay, so these aren't like fictitious things; they're actually numbers, which is a parameter to the neuron. So to put it in more precise algebraic terms, okay, and I will do that. Copy that here. I'm going to steal some of the language here because it's correct, really. I'm not just stealing it; I agree with it. So paste. Oops. Control Z. Right, and basically the algebraic terms were this piece over here, which is the output is 0 if we are less than this threshold, and it gets to be a 1 if the value is greater than the threshold. So that's basically pretty much it. So we sort of like, we compute these values over here, and we've got this number which is between 0 and 1, but then we have to decide, we have to give it a 0 or 1. We have to make a decision on that particular thing. So and that's what that function, that final like functional piece is. So but in the meantime, you just got a whole bunch of these things here that just have values between 0 and 1, and we might set our threshold, for example, to be 0.25, right? So 0.5 would now be classified as a 1. It'd be like an on, and 0.1 would classified as a 0. It'd be off. So it depends on where our threshold is and what that function looks like. But anyway, I don't want to be jumping ahead too far in terms of that, but I do want to put that in. So I wonder, like, yeah, I could kind of like sort of like do that. Okay, the output over 1 I'm just going to put this in here and I'm going to add it in as a formula again, but actually what I might do is take some of this, copy that, and paste it there, and then say something like equals, and then do where is it over there? If we've got our brackety sort of things, not that one, not that one. This is the bracket that I want, but it's going to be, I just want to do an open brace. So what I will do is, I can get away with doing this, which is that. When that condition is satisfied, and then that condition down there, I'm going to have to make this bigger now, because otherwise it's just going to look too small. Okay, I have to make the whole thing bigger. And I'm just effectively replicating this, but basically what we're going to get is a 0 if this is less than the threshold, and 1 if this is greater than the threshold. So over here the output is going to be equal to one if this is less than the threshold. And if I can nick all of this, because it's pretty much the same, apart from it's going to be a 0 with a greater than. I lost that. There we go. Again, the nice piece about this is once you've sort of like built it, it's kind of like there. You can see I've built everything from there, but basically if we're above the threshold, we get a 1. And if we are below the threshold, we get a 0. So it's kind of like looking like that, and that's basically what's been. Hold on. Okay, 0 if it's less than or equal to the threshold there. So I have got it. I've just put them upside down, but that's cool. I should probably put it the right way around because we want it. It's clean to be ordered. So I wonder if I've got a less than or equals to sign there somewhere. Yeah, there we go. I've even got that. And this one is going to be a greater than. And like, do I have a greater than sign? No. Okay, fine. I don't need a greater than sign. I've got the arrow. Notice that here we've got less than or equal to, because we have to account for all cases, and then greater than. And there's no could you have another case where it's like a half if it's equal to exactly, like if you land on the threshold. So it's sort of like saying you can't land, you have to have if you land on the actual boundary, it's got to. So if we drew that and we had our threshold, and our threshold was here, so that is our threshold with whatever function we have. So we have some sort of decision function that kind of like looks like this. And what happens if we land exactly on the decision boundary? Now, is that going to be a 0, or is it going to be classified as 1? We're saying here that if it lands exactly on the boundary, less than or equal to this threshold, our threshold here, then this is going to default to a 1, and everything outside of that, so a little bit bigger, to do that, so everything a little bit bigger is, so all of these go to a 0, not 1, and all of these, anything on the other side of the boundary goes to a 1. So that's kind of like optically what it looks like. But let's go back here. Okay. That's all there is to how a perceptron works. Fantastic, that's it, we've done everything. We now understand what a perceptron is, or we understand what a neuron is. So that's a basic mathematical model. A way that you can think about the perceptron is that it's a device that makes decisions by weighing up evidence. Let me give an example. It's not a very realistic example, but it's easy to understand so you get a bit more realistic. Suppose the weekend is coming up and you've heard that there is going to be a cheese festival in your city. I do remember reading this. I read this years ago. you like trees and you're trying to decide whether or not to go to the festival, and then you've got some decisions that come in here. Is the weather good, right? And then does your boyfriend or girlfriend want to accompany you? If they say no, then you're less likely to go. If the weather's good, then you're more likely to go. Is the festival near? You know, which i.e. is it convenient to get to the festival or not? So you've got all of these different factors that come in, and you've got these values that you attribute to them, right? And then you've got some sort of weightings that are based on them. So we can represent these three factors by corresponding binary variables. So we can give these things a number x1, x2, and x3. So this one here is going to be x1, and this one here is x2, and in this like rubbishy example, this one here is x3, right? For instance, if we have x1 equals 1, so if the weather is good, and for instance, we'd have x1 equals 1 if the weather is good, and x1 equals 0. So basically 0 here for bad weather, and you know, over here 1 for good weather, right? And likewise here, it does like the proximity of the boyfriend and girlfriend. Again, you're going to have a 0 or 1. We're going to have these choices, 0 or 1. And so we've got our values that all have zeros and ones. We've got all of them. Oops, I'll hit undo there for a second, but let's just keep scrolling down. Now suppose you absolutely adore cheese, so much so that you're happy to go to the festival, even if your boyfriend or girlfriend is uninterested, right? And the festival is hard to get to, but perhaps you really loathe bad weather. So you can sort of like see, like all of a sudden over here, we can assign these weightings, right? Now this one in this particular example is going to have this weighting here. So this is going to be the W's, and our W over here is going to have this high weighting. I don't know, it's like 10. And here it's going to be like really low weightings. Like you could even have a 0 weighting, by the way, but I put I'll put a 0 here. It's got no weighting. You actually don't care if your boyfriend or girlfriend goes. And then here you've got a W equals 1 down here. So sort of like a low, like is it like if it's a million miles away, maybe you won't go. Otherwise you will definitely be going. So all of a sudden we have like our values, and we can make a decision. There's a neural decision that's already being made here. So but perhaps you're okay, fine. Use these perceptrons. You can use perceptrons or these nodes, these neurons. You can use these perceptrons to model this kind of decision making. One way to do it is to choose a weight. W equals 6 for the weather. There we go. He made his W like not as large, and W equals 2 for the other two things, for the other conditions, because they had like lower meanings. The larger value of W1 indicates that the weather matters a lot. Okay, that's the weight. It matters a lot. So we've turned that W into this matters a lot. We've turned that, and kind of like when you do like really low level maths, it's GCSE maths and stuff like that. Like you get this a lot. So like this matters a lot bit. What does it actually mean? Well, it actually means matters a lot means that W is large, right? And if it didn't matter that much, then I don't know where. If it might, maybe it says matters less, but then W would be small, right? So mathematically, this set of words here translates mathematically into either W large or W small, and in our particular case we're told that W is large because it matters a lot. If it doesn't matter very much, would be W is small. Anyway, matters a lot to you, much more than whether your boyfriend or girlfriend joins or the nearest public transport. Finally, suppose you choose a threshold of 5 for the perceptron. Okay, so finally, after we've done all of that, like we can compute our weights and biases, which is the Wi in this particular notation here is the Xi's, right? Now we say, well, we want to know, like whatever this value is, we don't even know what it's going to be, but is it either greater than or less than? So is it, if it's greater than, you know, whatever we decide here. So like our threshold value, I won't even use a 5. I will use a like T, I guess, for threshold. I don't know what the formal thing is for threshold, but I should just use a T. If these sum of the wi xi's, which is from I equals 1 to n, in our case is only 3 of them, so you know, if I was to put this sigma here, this would be I equals 1 to 3, just to show the full notation. So that's w1 times x1, w2 times x2 plus w3 times x3. If the sum of all of those is less than whatever this threshold value is, then or greater than this, then we're going to go. So we're either going to go, or the other decision is obviously if it's less than or equal to that, then we are going to stay. Right, there we go. Right, so we've made our mathematical decision. We've translated all of this language now into maths. So let me remove all of those. Finally, suppose you choose, okay, fine, with these conditions, a perceptron implements a desired decision-making model, outputting 1 whether the weather is good, 0, it makes no difference to the output whether your boyfriend or girlfriend wants to go or whether the public transport. Yes. It makes no difference to the output whether your boyfriend or girlfriend wants to go. Well, it actually does in this particular model here because it's got a weighting of 2. So in that particular case, it does have a difference. But anyway, by varying the weights or whether public transport is nearby, but if you didn't want to have any weighting, maybe it mentions it here and I've skimmed it or missed it, but if you didn't want it to have any bearing whatsoever, as in I don't care if my boyfriend or girlfriend goes, or I don't care about how far I am, I'll just set these values to 0. That's basically what you're going to do. So that now your decision will be fully made based on this, because literally you've got these perceptrons that are coming in, which is, you know, these nodes that are coming in, that are coming into this node over here, and we had these weightings over here like this, that one, and that one. But it's literally like saying, well, actually, I don't care about the last 2, so remove them. Get rid of that, get rid of that. There we go. I only care about that one because these ones now have 0 weighting. That's a 0 weighting, and that's a 0 weighting. It's got no weighting, and this one now has a 6 weighting. All of the DW, or like all of the DC, the change in my cost function now relative to relative to my weights, the entirety of it is actually dependent only on this. Like that's the sole criteria now, if I set that to 0. But anyway, that's the maths of that. So by varying the weights and the threshold, we can get different models of decision making. For example, suppose we instead chose a threshold of 3. Again, we could choose our thresholds too. We're not just managing the weights and the biases, but we're also managing the thresholds as well. So then the perception will decide that you should go to the festival whenever the weather was good or whether both the feather. So we get the idea of it. Obviously, the perceptron isn't a complete model of a human decision making, but what the example illustrates is how perceptron can weigh up different kinds of evidence in order to make decisions, and it should seem plausible that a complex network of perceptrons could make quite subtle decisions. And that's kind of like the interesting part of it, is that we've got these inputs, we're just going to go and collect them because it's sort of like real world data, and we're going to pass them into our system, right? And it's sort of like real world data in the sense that, like, you know, what is this number, right? It's a number 8. It's great that I can't write really well, and it's sort of like, what is this? It's sort of like this over here is a 6. You know, why is it like, and there's some decision that we've made that this is an 8 and this is a 6, isn't it? It's got 2 loops here. It looks like it's got 2 loops. Here's a top loop and here's the bottom loop, right? But now we sort of like no longer care. We're just passing this into our model, and we're saying kind of like that this is and it's going to go and do a lot of complicated stuff under the hood, and then come out with this subtle decision, like as in it's making this decision through the neurons, as in like if there's more stuff in the top corner or something like that. And it's going to make these decisions and sort of like categorize it and break it down into smaller pieces. And don't forget, we don't have to have just one, just two layers here with an output over here. But we could introduce another layer in here and another one, and the number of computations goes up a lot because each one of these inputs here goes to this. So that you can already see 1, 2, 3, 4, 1, 2, 3, 4, 5 inputs, and three nodes over here. Well, that's 15 arrows over there because it's 5 times by 3. And then like for every one of these and so forth. So like there's tons of, if you like consider any path, this thing can go one way, 2 ways, 3 ways, but it can go, it's got loads of paths. It's got one path at the top, then it's got a second path, 2 paths here, then it's got a third path here, then a fourth path here. So it's got 4 options there, 3 options there. So it's got 12 routes. This particular thing over here has got 12 avenues before it arrives at the output. It's 12 computations before, imagine we introduced even more things. So we've got 12 times by 5, which is 60 avenues, because there's 5 of them, 1, 2, 3, 4, 5. So you've got 60 like computations. And that was only on a 3 by 2 or whatever it was, 3 here and 4 here. So we can see if we had like 100 in there and whatever, like it's gonna, like these numbers will balloon out quite a lot. So I think that's kind of that bit. We're going to get these subtle decisions. Anyway, there's a lot to go on here. In this network, the first column of perceptrons, what we'll call the first layer of perceptrons, is making 3 very simple decisions by weighing up the input evidence. What about the perceptrons in the second layer? Each of those perceptrons is making a decision by weighing up the results from the first layer of decision making. In this way, a perceptron in the second layer can make a decision at a more complex and more abstract level than the perceptrons in the first layer. So we don't even necessarily need to know what it's doing, but it's doing something based on the weights and the inputs, or the biases, I guess we'll call them. And even more complex decisions can be made by the perceptron in the third layer. In this way, a many-layer network of perceptrons can engage in sophisticated decision-making. And I built a neural network actually for funds management stuff, and it was actually better than the humans by far. And then they didn't want that because they said, "What's the purpose of it?" I was like, "Well, it's sort of like replacing all of our jobs," and I'd go away. We don't want that. But it was just fantastically powerful, basically, and it could take multiple inputs really simply, like to take like 30 or 40 different input parameters, which is all the sort of things that we might have looked at on a fixed income desk, like take the coupon, the maturity, like something that's got a longer maturity has a higher weight and it's got a shorter maturity as well, and pass it into this model, and this model can do some really complicated things. And whenever you say like, "Oh, has it considered that?" It's like, yes, it's considered in, it's in the model. And all you then have to do is start calibrating your model to get whatever you want. Anyway, aside from that, we've got our simple, more basic example here. Incidentally, when I define perceptrons, I said the perceptron had just a single output. In the network above, the perceptrons look like they have multiple outputs. In fact, there's still a single output. So over here, I guess it looks like this one has multiple outputs, but really it's just one output, and that one output is being transmitted to the 4 different items. So it's the same value that goes out 4 times. Now there might be 4 more weights on it, but that one output is going out 4 times. The multiple arrows are merely a useful way of indicating that the output from perceptron is being used as the input to several other perceptrons. So again, it's just kind of like being said. It is less unwieldy than drawing a single output line which then splits. So you could choose what you wanted. And what it's really kind of like saying is, I guess maybe I could introduce a drawing, but this here is just one value, so I might do it as a new thing. So each node, which we might call each node or a perceptron, has just one output. value that is transmitted many times to the nodes perceptrons in the next layer. And it looks like, if I can do a drawing sort of like new, I wonder if I can steal some of this. Let's have a look. I don't know, I'll end up deleting a lot of it, but if I just take that and kind of like, again, we're sort of like using the benefit, like we have a cost to doing this, so we might as well use the benefits of it. We've got this, but well, I could actually do this. Maybe I can do this, which is right, what he's actually referring to there. I wonder if no, I don't have that. Elbow connector. Great. Well, I could do multiple elbows, but I wonder if I could also like make a little splitting point shapes. I'll make the tiniest little dot somewhere. And there we go. And then we're going to have this one line going in here. So that's what goes there. And let's get this little arrow there because I want us to like move it horizontal, so it's horizontal. Annoying that is. Okay, but basically this now goes right. It's only the point being that this is only one value. Let's do another line here, that one, and then that one. I don't even care how they look in a way. I do care, but I don't care. Oops, Control Z. Let's get our elbow connector. Oh, that's ugly. Why is it doing that? I wanted to get that little node. Ah, it's because I got the arrow on. Maybe I'll just do that again. Let's try it. There we go. Okay. And then another one. Which will go here. So you sort of like get the idea. They aren't just arrows, but they are exactly that. This is the only ugly one. I wonder if I can click on that. I sort of like, there we go. Yeah, I can do that. And continue, so forth. I'll do ... or something at the end of it all, but because we want to go down here and sort of like at least get to our last one, which is that over there, and then kind of like, I guess it's just doing that, and so that we understand that it is ... like that, triple dot. There we go. Dot. There you go. And save and close. So there's just one output here. This has just got a value of between 0 and of either actually 0 or 1, and then we're going to have a whole bunch of weights. So that one value here is 0 or 1. So I'll actually write on there, because a decision has been made, like the weighting has been collapsed. So here we have a 0 or 1 over there like that, and that's going to go over there somewhere, and with a little arrow, let's copy the colouring of the arrow, copy and paste that, So like point to this line here and point to that over there. There we go. And now there we go. That's the best I can do to, because it's snapping it to the grid. It's really annoying. Actions, rotate, guidelines, snap to grid. There we go. Maybe that's a little bit there. There we go. So anyway, I'm pointing to that particular line, not to the actual grid. But anyway, that's what it does. So we've got an 0 or 1. And it's only one value. It's either 0 or it's 1. And it goes to all of these J neurons with the different weightings W, W1, W2, W3, and so forth. So maybe I'll stick the weightings in as well, which is the W. I think the subscript was it shift in that? W1. Let's have a look. No, it's got a less than sign there. W control dot. That was a superscript. That one, W1. So that was one of the weightings. And then we're going to have a W over here. That's going to be a 2. And it's like neural weighting, but that's W1. And then that's a W2. See where we're going with this? Yeah, good. And then, you know, dot, 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 and whatever, copy this one here. But finally, we're going to have a W. And hopefully that, I guess, beginning to make a bit more sense now. We can do a save and a close. So we have this one value, 0, 1, and we're now transmitting it into our next layer. And we could have subsequent layers after that, but these next layers will have these weightings, and we can make this much more complex decision now. So let's just go and have a look a little bit more. It is less unwieldy than drawing a single output line. Okay, fine, and that's what it was. So we've got like both versions of it now. Let's simplify the way we describe perceptrons. A condition W of the sum of the all of the J items of Wj to of Wj xj needs to be greater than this threshold is cumbersome, and we make we make two notational changes to simplify it. The first chain is to write Wj is the dot product, and this is standard maths, right? So I'm going to put this in, right? Yeah, I'm actually going to put the whole thing in here. I'm going to have to copy some of, remove some of this. This is understood mathematically. This is, it's nothing to do with like this. Again, we couldn't talk to each other if we didn't have this. But basically, and this is a good thing about copying some of this stuff, which is somewhere. There we go. This condition is cumbersome, and we make two notations to simplify it. The first, and I'll put a list these out basically. The first change is to write this as a dot product. So, okay. So we can say here that go back to the beginning, but WK, we now can just say that WK is, we can use this equivalent sign over here, but is equivalent to all of that. So I'll put the little dot there. I think he had the little dot in his one, but basically this means that this is a vector, this W is a vector, and this K is a vector, and we now no longer need this long notation here, because we can just say that WK means all of that, which means the sum from I equals 1 to n of the WIKIs, right? Where, and it's got it right here, where W and X are vectors whose components are the weights and inputs. So basically, W will look like, really I should write a vector in a vector way. New equation that W is equal to, and then do we have some vectorized looking thing here? Not really. Okay, but okay, you know, Pythonically at least, if we're talking about, and I can do this, I'm just going to write my vector horizontally, but W is equal to W1. Actually, there we go, I was outside of the thing, so I could actually write it all just in that, because I probably don't need to have that, but I'll do it, which is delete that one in this thing here, which is W1 comma and then W2 comma the ellipses, and then finally paste that in here, which is our Wn. So basically it's a vector that looks like this. Now really we write our vectors vertically. I'm not sure that I've immediately in the equations got the capacity to write. I wonder, no, you put your vectors in there and you sort of like list them downwards. Yeah, I don't have the capacity to do that, but we can, I guess I'm hoping that we can understand that. But likewise, these are also the K's. It looks exactly the same. So that's pretty much it. Each K we can see here, or well, I should put, I don't know, am I keeping it right? It's going to be our J's actually in this particular case. The first thing, okay. I've got to be careful with the notation. Well, it's fine. Okay, well I can keep it like that, although we could understand that the J's would also be the same, but basically every weighting here has a weighting here, and it would refer to the J's here, but like just for the purpose of the notation, it's fine to understand its case. I wonder why I had that there in the first place, because that was talking about the earlier weights over there that needed to be above a threshold value. And that's not coming from the K's actually. That's the weighting of the K. That's actually the weighting of the Jth item. So I've got to be very careful about that. Oh no, this is determined by the WKs, because that is. But really, what we've got is a. Oh, it's a WIKI actually. Yes, it is, because it's the weighting of this one, and then it's the weighting again of this one. But I've got to be careful because what I refer to. But anyway, I think we get the idea of it. But we do have to, like, just as long as we stay consistent with mathematics when we come to doing it. But we've got our notation at least working over there. So let's continue then using biases instead of, okay, right, anyway. The first change is to write the, okay, as a dot product. So we're using the dot product. really standard in maths, where W and X are the vectors whose components are the weights and inputs respectively. The second change is to move the threshold to the other side of the inequality. Okay, fine. Oh, and also the bias, that's what the bias is. So I've got to be careful what I call as biases. The bias is, the bias is referring to the threshold. So that's why I needed to be a little bit careful. I wasn't 100% sure on it, but now it's got it here. So it's classified it. The second change is to move the threshold to the other side of the inequality and replace it by what is known as the perceptron's bias, or the threshold, right? So where I drew my original thing and I had, I used the letter T over here, we needed to have like the W. Can't write W properly there, but basically we needed the W, I, so like Ki or Xi's depending on what we're talking about, but basically the Wi, Ki, we wanted to get it to be greater than this threshold, or less than or equal to this threshold. Now this threshold here that we're talking about is actually the bias. It's actually the negative of the bias, so it's basically minus b, basically, is what we could replace threshold by. Now if it's greater than t, then it needs to be less than minus b. I think it flips the sign the other way around, but that's pretty much it, really. So let me just put that in, because that's very important, because that's the only two things that we talk about. So the first change, I will embolden it, and the second change, right, is to move the threshold to the other side of the inequality and to replace it by the perceptron's bias. X there, I'm going to see a new equation, and then B equals, I won't even have to do that, but B is basically equivalent to minus the threshold. Using the bias instead of the threshold, the perceptron can be rewritten, and now I can sort of rewrite the formula, and I can go and take this formula over here and paste it straight down here. So much of mathematics is substitution, copy and paste, and now we've got, where we've got threshold, we'd have a minus b. And a minus b over here. But we will take this minus b over here, because negative, we can add it to the other side. So we can do x and paste it here, and it becomes a positive on the other side. Okay, and that's going to now be less than 0. And likewise, we can take this one, x, paste it over here. We've moved it from the right to the left, so it's got to become positive, and that's got to be greater than 0. But not just that, we are now, if we can replace all of this expression with the WK like that, so we can say the dot product of W and K. Copy, and I think that's what was in the notation. That's where it all actually comes from, and that's really nice and cute. I'm hoping that I've got that. There you go. If Wx is plus b is less than 0, everything's consistent. It followed through. I just literally did a copy and paste of the above mathematics that we kind of like, or the framework that we sort of like agreed on. I changed threshold to minus b. I was then able to move minus b from the right hand side. I could add b to both sides of the scale in our really basic mathematics, right? When you're little babies and you do mathematics, really what you're actually doing, moving from left to right, is you're adding a b on here. If I add a b to this side, I have to add a b to this side, otherwise the scales won't balance. but I had a minus b on this side, so I cancelled out. I started there, so I was left with this cancelled out to a 0, and I'm left with a plus b over here. So our equivalent operation on both sides is the way that we move it across. There we go. So Maths 101. You get to learn the most fundamental of mathematics when you do this. And all these neural networks are exactly based on that. It's like pure fundamental maths. So we've got that. That's really nice, a nice looking formula. And I think that's that. I'm not using LaTeX. I'm using this like really simple equation editor in Google Sheets. Like, so it's the bare bones, but it's good enough to depict what we want, and that is our equation. Now, you can think of the bias as a measure of how easy it is to get the perceptron and output to an output, a perceptron to output a 1. Or to put it in more biological terms, a bias is a measure of how easy it is to get the perceptron to fire. Okay, this is your on decision, like I'm going to make an active decision, and if I lower this threshold, so if I lower this bias, then I'm more likely to make that happen. Now, I might be like, I don't know, if I'm a rabbit, then a little piece of movement might trigger me running. So my threshold is low, as in my bias is high, because bias is, or my, I guess I'll just say my bias is high as well. I'll just keep them like equivalent for now. But basically, like that value doesn't need to be that much for me to be very twitchy and jump. That's all. So for a perceptron with a really big bias, it's extremely easy for the perceptron to output a 1. That's basically it. So, but if the bias is very negative, then it's difficult for the perceptron to output a 1. So it's exactly like the twitchy rabbit thing, and the bias is the negative of the threshold. As in, if I had a low threshold, I put into really, like the low threshold would equate to a really high bias. Obviously, introducing the bias is only a small change to how we describe perceptrons, but we'll see later that it leads to further notational simplifications. Because of this, in the remainder of the book, we won't use the threshold, we'll always use the bias. So one thing that we need to remind ourselves or say is, or this is important, kind of like that the bias is negative threshold. We'll always to the bias for, as opposed to the threshold for consistency. Otherwise, we're talking about two different things, two different variables, which means the same thing. So, yeah, I guess that's that. I've described perceptrons as a method for weighing evidence to make decisions. Another way perceptrons can be used to compute the elementary logical functions we think of as underlying computations, functions such as and, or, and then. For example, suppose we have a perceptron with 2 inputs, each with weight -2, and an overall bias of 3. Here's our perceptron. Then we can see that the input 0, 0, and 0, 0 means x1 equals 0, x2 equals 0, produces an output of 1, right? Why is that? Because you've got 0. Let's have a little think about that actually. We see that the input 0, 0 produces an output of 1. Oh yeah, because we've got the bias of 3. Hold on. Since -2 times 0 plus -2 times 0 plus 3 equals 3. Okay, yes. So we just got this positive number. That's it. And that's why we got the 1. But basically the maths follows it. Here I've introduced the times symbol to make the multiplication explicit. So this is the wi, and this is the xi, and then again the wi and the xi here. So that's the sum of the wi xi's, and then plus the bias at the end, which is I guess, okay, that's the value that goes in, and we're comparing this 3 to and an overall bias of 3. Okay. So we get our 0, so this computes to 0, and then we add on our bias, and then we get left with this value, which is 3, and we're saying that 3 is greater than 3 is positive. So this is either going, if it's greater than 0, that we're going to give ourselves a value of 1, and if it's less than 0, we're going to give ourselves a value of 0. It can only be one of those two, and because it's 3 in our particular case, the mathematics works out quite nice. So we've only got this pair, basically a 0, 1 pair. There are two binary outputs from any particular neuron, and that's basically it. But input 1 1 produces this, right? So let's have a look. Why does the input 1 1 produce that? Because we're going to have a -2 times a 1, which is -2, and then we're going to have another -2 times a 1, which is -2. So now we're going to be left with a -4 here, and then we're going to add 3 onto -4, so we're going to be left with -1, and that's negative. And so our perceptron now is a NAND gate. The reason why, I guess, is because all of the different options that you can put in. Like let's just say that we can only put in, and this is, I think, what this is referring to here. We can make a little table of our x1 and x2 over here like that. Make a little table. It can only take these values 0, 0. You can only put in these things 0, 1. 1, 0. That's 100% of everything that can be put in, and 1, 1. There are 4 things, and each one of those produces this output here, OP for output, right? So a 0, 0 produced a 3, right, which then transmits into an on, so a true, basically. We did the 1, 1 here, which ended up being a -1, so that was false. I can't remember what an AND gate is. Someone will have to remind me what an AND gate is. I'm going to type a little thing here. Reminds me what a NAND gate output. Please, there we go. There we go. But basically, an AND gate is if this and this are true, then that will be true, and then all the other ones will be false. So a NAND gate is if this one and this one is true, that is false, all the other ones will be true. I'm presuming that all the other ones here, correct me if I'm wrong. I mean, we could inspect it and find it out, but you can basically make a logic. I'm asserting now that these ones are both true as well. There we go. That's what a NAND gate would be. But anyway, he's saying that that's it. I'll go and do the mathematics of it. It's quite easy, right? 0 times -2, well, that's 0. 1 times -2, well, that's -2. See how, like, he's chosen this quite well. So we've got -2, then we're going to add on our bias, which is 3, which is +1, and that's a true. And likewise, that one's going to be a true. So there we go. With a final decision. Right, that's our decision. So we had our inputs, we had our biases, we were able to do our full computation, and then we came out with this decision, and we could say, like, if we did have a weighting of -2 and -2 and a bias of 3, then and a bias of 3, so then we would with this particular system here would actually produce an AND gate. It would be an AND gate. So we can now use these perceptrons amazingly well. I was going to copy that, but it's probably not the best thing to copy. Like, it's a little bit ugly, but That's quite interesting because I never thought of it like that. But although I did read it at some point, I don't know, maybe I brushed over it. The NAND example shows that we can use perceptrons to compute simple logical functions. In fact, we can use networks of perceptrons to compute any logical function at all. You can perceive this like, because you can construct this in any way you like. The reason is that the NAND gate itself is universal for computation. That is, we can build any computation out of NAND gates. I can't remember that from when I was about 10 years old doing GCSE technology. You have to like put the gates together, but basically the NAND gate, you can make all other gates with a NAND gate. With these different, I think, with these different combinations of gates and funny ways of doing it, but you can do it. So it looks like the neural network has the same version of it. So I might actually add that in here, which is we can use a network to construct a logic gate like this, right? And then I'm going to sort of like go through it. I'm going to do the mathematics of it, which is an example of a NAND. Right, so I'm going to have an example of a NAND gate, but we can construct all other logic. Also, either with the mathematics of, and I might actually like, I don't know if it leave it as an idea, but like you definitely leave it as comments. Like, can you construct an AND gate with a very simple neural network setup, like one neuron setup? So two inputs that come in, and then whatever number, a bias that goes there. So like, can we construct an AND gate? This is the question. Here's our inputs. Here's our node, and we've got these weights, W here and another W here, so W1 and W2, and we've got some sort of bias that we're adding onto that. Can we construct an AND gate rather than an AND gate? Right? Is there a set of numbers? Is there a bias? So which bias would we need, and which weighting? So which W, I, and B and bias is required, right? That's kind of like a question. If anyone knows the answer to that question, fantastic. So anyway, I'll continue there. So I'm going to do an example of an AND gate, but we can construct either with the mathematics of the node, either with the mathematics of the node or with the fact that we can use NAND gates to construct all other logic gates. It's important, by the way, quite fundamental in computing. I can't remember the combinations of them. He's got a drawing of it. I'm sure that is the drawing of it, that we can do like other computations, or not other computations, but construct any other gates. But let's just go through the NAND gate, and like I could sort of like steal his imagery, but I think I kind of like remember it. But we could make our own construct, possibly. We can that's not the only construct, I imagine. So So I'm now going to, in real time, attempt to build a NAND gate, a neural network NAND gate, and I might forcibly make my one different from his one, which is that basically I am going to steal some of the ideaing off of it, which, okay, he's like, so like, I'm going to steal a formatting. He's only got one circle there for the neuron. Now, let's go back. I'm just trying to think. So I've got, this is my, I will keep the neuron or the node as a circle. I should keep that one as a circle there. But basically over here, I will actually, I'm going to be different, I don't know. Even the inputs should really be, I'm going to say that they are to like numbers there. So you've got something here, and copy and paste. You're going to have something down here. And now we've got to have these two weights that come in. So this goes to there, and again got another arrow. This one goes to there, and this is going to be. I'm actually going to use our formatting, our like notation here. I'm going to stick with it, right? So K. Now we've only got, this is going to be K, this is going to be layer 2-1 basically, but this is, we've only got one item in the J's and the K's, and the K's are the early ones, so K1, K1, right, is going to make this small enough that it fits in. And that's basically K2 over here, and I can take that as well. W1 and it's going to be W2 like that, and then we're going to have a bias. So I might just write the bias somewhere. B for bias. Bias. Right, we've got a bias over here, so we're sort of like introducing a bias, and what we're going to have is the WY KI. So, and this is, maybe I'll take the opportunity to do the vectorized version of this now. Copy that, paste that over there. Maybe I might be able to stick them all in, but K1. And then I hate it when it self-capitalizes, K2. Okay, there we go. That's K1 and that's K1, K2 vector. And we can sort of like see the dot product here, W1 and the W2 vector. And then we're going to have each one here. The bias is consistent, so no B1 and B2. It's just going to be a bias B and B like this in mathematics. So we got this vector, and can I do? I wonder if I got shapes, arrows. No, do I have anything like brackets here? Call it equation. Oh, here we go. Oh, that looks good. That's what I wanted. Got a little piece of mathematics going on here. That one multiplied by, I'll bring them out a little bit so they're not like on top of that. Move that one out of the way for a second, just put the brackets around it. In our dot notation, the mathematics looks like this. I won't even put the dot between it, but that's the dot product. And finally, I didn't want the W's, I just wanted the brackets. Yeah, I've got the brackets there that time. And I will have to introduce a plus sign now, so let's just go and do it. Shape, equation, plus. Big fat plus there. It's a bit ugly. Let's see. Why not? This is literally the mathematics of it now. And then we're going to finally get a equation. We've got the equal sign there is equal to, well actually, it's the sum of all of them. They're going to compute to one number now. So we can now say that just say here that W1 and W2 is equal to and then we're going to say common naught, right? If we say minus 2 and minus 2, so that's what we're saying. And I'm going to shrink these down because they're not capital W's, just W's. So if we say W1 and W2 is minus 2 and minus 2, then they're the weights, and these are our actual node values. They're our inputs. So over here, which is right, so they're our weights, and then we've got our inputs, which I might take this notation now. So our weights are the W's, our inputs in this particular case here, for the purpose of the notation, are going to be K1 and K2, and they will be set to whatever values that we want. So for example, let's say we put in a naught and a naught to start with, because that was one of our examples, but our inputs could have been all of these things. So mind if I can make this bit a little bit longer, because basically the inputs are going to be the exact table that we constructed, which is going to be that one there. So that's a 0, 1. Then again that one there, which is a 1, 0. And finally this one here, which is a 1 and a 1. Right. And I'm going to have to move the, I don't want that one. There we go. I'm going to sort of shovel this all across a bit. So we got our inputs over here, and then we've got our weights. I'm going to keep our weights sort of like over here, I guess, right, because this is how it actually works or looks. Then we've got our mathematics over here for the computation, the decision making, should we say. That's what we're going to do, and we're going to compute our results, so basically our outputs, remembering that the output can only take two values, right? It can only be a true or false, or a 1 or a 0, basically. So output, and what we computed, or what we got, I believe, was a true. In fact, we got the full NAND gate thing because we did the calculation of it. But I'm going to actually put the numbers in afterwards, I think, just to be clear. That's a true, and that was a false. Right. I'm going to embolden this here. I'm going to embolden this here. Right. I could embolden that there. That's our weights that went in. This is our well, we had our biases over there as well, bias B, and this is our decision making. But basically what we actually had was we set our bias to be equal to 3. In our particular case, the bias was 3. So it's now looking a bit more like the format, but what I wanted to get here was basically the actual maths of it, which was 0 times by minus 2 plus 0 times by minus 2 plus the bias. So I might have to squeeze this in. I wonder if it will fit, plus the bias, which is 3. Plus 3 is equal to, I have to change the size of all of this pretty much. Right, is equal to 3, and that gives us a true. And then all of this, copy it there, because that one there is a 0 times a minus 2, which is 0, then a 1 times a minus 2, which is minus 2 over there, and I don't know if I've got space to put it all in brackets, maybe I will, but that minus 2 and then plus 3 is going to be equal to 1, and that gave us the true basically. Paste that one here, and this one was now 1. This one was a 0, so you got exactly the same stuff. And finally, on the last one, I can actually even paste it here because this is just a 1 here, and this is just a 1 here, and that gave us minus 2, which is minus 4, plus 3, so I'm left with a minus 1 over here, and that gave us the false. So that was all of our outputtings, should we say. There we go. So that leave a little gap. Right. Extend it a tiny bit more. So sort of like our result there. Right. And if there's like a better way of doing this, or sort of like more colorization or something, not border color over there, but border font, not the font being when it's color, fill color, border color. I don't know, because I've zoomed in so much. Oh, there we go. Highlight color, text color, there we go. So I wanted to get that sort of like blue. Didn't pick blue there, pick purple, there we go. Blue. Copy, paste that, and paste that, and call it false. Right, there we go. Maybe I'll turn that one into a sort of like purple there, just to differentiate the color. Save and close. Right. Now we've got that. Right, so it's an example of an AND gate using a neural network, a very, very simple neural network with only one node, and the weightings are set to -2, -2. I could have put the weightings in this format, like this vertical format, but we can understand that this sort of means the same. That's cool. And that's pretty much it. Fantastic. So I think there's quite a lot done. I wasn't expecting a lot done, but sort of like one step back, but then quite a nice complete step forwards because we got a good understanding of it. And I might leave it there just because we're at 2 hour mark. So this is becoming a long video. So I sort of like leave it there. So it's nice to leave it where you're on a high, because like that's quite a not so like nice computation to come out with. You know, I'll probably forget what all of this is. So like go like, oh look, I need to put brackets around here or something and whatever. But maybe I'll complete that in another section, as in when we come to do the recap. But the next question was. So here I'll leave a question, an open question, which is, can we construct, or can somebody like who's watching this video, who's managed to get to the 2 hour mark, can we construct a simple AND gate? An AND gate using a simple I'm calling it a neural network. The mathematics of a simple neural network, question mark. So can we construct an AND gate? Or an OR gate, right? So I'm not going to do the XORs or whatever, or the well, we had the NANDs, but not doing the exclusive or an OR gate, but just an OR gate. Can we do like the simple ones using the mathematics of a neural network? So that's like an open question. You know, maybe I'll have a little think about it myself, sort of like. But basically, by changing the way the simple neural network, by changing the weights and biases, the weights W, not the biases, the bias, because there's only one bias. There's one bias that applies to the actual next node, but there are multiple weights. And then we've got the inputs that are coming in here, the input layer, effectively. And I could sort of like write over this and sort of like this piece here is the input layer, right? Input. There you go. Spelled so terribly. And then we've got some sort of decision computation here. This is our computation, or the decision. And finally we get the output. So we've got something, 8 processes done on it, which is the KI, WI plus the B that we're seeking, such that our criteria over here is satisfied, and it either drops down to being less than 0 or greater than 0, and inputs us a result, a decision of a true or false, or 1 or 0 based on that. And that's pretty much it. So I think I'll leave it there. If you like this video, hit the like button, the thumbs up button, the follow button, and all the rest of it. And even if you didn't like the video, still hit the thumbs up button, like button, follow button, and all the rest of it. If you do have an answer to this AND gate, that would be fantastic. If you could post some weights and the bias in there. And yeah, I think that's basically it. So I'm going to sign off, and thanks for watching. Stop streaming.